Yeah, I'm going to make up a problem. I'm making up a problem of dE y double prime plus 9y equals, and then I want to make it a piecewise problem. It's going to be I think it's going to be the sine of 2t, and that's going to happen for the first 2 pi. And then it's a 0 after that, after t is greater than 2 pi. Yeah, this is a good problem. It's a higher order dE, and it's got this non-homogeneous side, but anyway, it's got this piecewise side, so half the problem is non-homogeneous, and then half the problem is homogeneous. And we want to solve this piecewise problem. I should put some initial conditions on this. I really should. Y of 0 equals 2, and y prime of 0 equals 1. Okay? All right. That sounds like a problem. This might take a whole hour right here. All right, so what do? The truth is I kind of wanted to work on this, the non-homogeneous part and but you know what you do. Even when you do the non-homogeneous part, you pretend for a second that it's homogeneous. So right off the bat, I'm pretending it equals 0, and I've got this. M squared plus 9 equals 0. And I get my roots pretty darn easy. I move the 9 over, and of course I get my plus or minus 3i. And I'm ready to write my answer. Boy, maybe it doesn't take an hour. I'm going to go here. My answer is going to be over here. And the truth is, so with a 3i, hang on, I got to get organized. So for the top half of this problem, the answer is a yc plus a yp, right, you guys? Yep. And guess what the yc is? The yc comes from this, and it would be c1 cosine 3t plus c2 sine 3t. Okay, that would be the yc. Okay. I think I'll just sort of put that up there. That's C1, this is the answer. C1 cos 3t and C2 sine 3t. Now, there's going to be something else here. There's going to be a yp there, I guess. So there's more going there when t is less than 2 pi. What about when t is greater than 2 pi? When t is greater than 2 pi, it's homogeneous, and that's the answer. That's the answer.
Make it C3,
Except,
C4.
I do. They are going to be different C's, right? So you're right. So for the bottom part, this is the answer: cos 3t and C4 sine 3t. Okay. So, but there is this yp that I need right here. All right. So far, that's not bad. I got organized, and it's almost like doing this homogeneous part helps you do this non-homogeneous part, like we've been discussing. All right, well, to do the yp, it's not all that hard, really. It's a guess, and we've learned how to guess. I guess if it's a sine 2t, I think my guess should be A sine 2t plus B cosine 2t. That's kind of how you have to guess. A sine or a cosine has to be guessed like that. And we worked hard the other day. We had a lot of dependency issues. What we got to watch out for is any terms in the yp better not be linearly dependent on any terms in the yc. Are they?
Yes.
Yeah. No, they're not.
Nope.
Right. No, they're not. maybe you think it's kind of close. These are cosines and sines. These are cosines and sines. But no, specifically this argument is 2t, and this one's 3t. That makes them different. They're independent. They're linearly independent. I have no dependency issues when the angle's different. So that's good. This is my yp, and I guess I need a y prime and a y double prime. I sort of plug them in, and that helps me find a and b. Okay, yeah. You guys with me?
Yep.
Okay. All right, well then y prime, 2a, cosine 2t. That's, you do a derivative like that. Negative 2b sine 2t. What I really need is y double prime. Y double prime, subscript p. Negative 4a sine 2t and negative 4b cosine 2t. Okay. And then we sort of plug those in, although last class I was sort of doing a shorthand way. I was plugging them in sort of in my head. And what I'm doing is I'm plugging y double prime in there. I'm plugging y in there, multiplying by 9, and somehow I'm trying to equate it to this right-hand side and equate the coefficients of the like terms. And when I do all that, I'll find a and b, I hope. So the way I like to kind of do it is start with the term that is there. I want to look for all the sine 2t's. And let me just remind you, what I'm doing is I got one of these y double primes, and then I got 9 of these y's. I mean, that's what I'm adding together. I'm really not using y prime at all. There is no y prime in this problem. Okay, so here I go. I'm looking for the sine 2t's. Well, here we go. We got negative 4a. Up here we got a 9a. Okay. Negative 4a and 9a, and that should equal 1. Okay. You guys all right? Mm-hmm. So that's 5a equals 1. Cool. A is a 1/5. This is interesting. We did one just like this the other day, kind of with sines and cosines. I think the cosines are I think I'll probably have none. You know, what's going on here is because that y prime is gone, you notice that the y double prime and the y are both sine functions. The y, well, anyway, there's something going on here. You know, if there was a y prime in this problem, there would be some b sine functions. There'd be some b's, and there wasn't any b's. So in my anyway, here we go. Cosine. Negative 4b, and up here 9b, and what does that add up to? 0. That's 5b equals 0. No big deal. B is 0. And so I know my yp now. Here it is, right here. It's this original yp. The b is a 0, and the a is a 1/5. So I think I'll just put that in right over here. 1/5 sine 2t. You guys all right? Mm-hmm. Still all right, okay. All right, cool. So that's cool, you know, we did it, we're done, we solved the DE. I think here comes a lot of work though here at the end. I think there's a lot of work involved here to try to find the C1, the C2, the C3, and the C4. You know, notice something here. The initial conditions are right here, and they happen when t is 0. Well, when t is 0, where are you in this piecewise function? You're in the top piece of this piecewise function. And so those initial conditions kind of apply to this top piece, and therefore I think they'll help me find C1 and C2 is what they'll do. And then I'm going to need to figure out a way to find C3 and C4. Now, there was a method we kind of used. So the initial conditions help me find C1 and C2. Setting this equal to each other at 2 pi, what you're saying when you say that is we're making this continuous. And making it continuous at 2 pi is a concept that helps me find C3 and C4. Except,
don't we still need another function?
We do need something else. Yeah, I mean because there's now 2 constants.
Take a derivative to make equal as well.
Yeah, how'd you know that?
Guess.
You heard Joe say that?
I was going to say that too.
You were going to say that, and it was a guess, huh? That's a good guess, because that is the hint. Right. I want to write some notes here. I want to say this. I want to say that initial conditions will help you. Will help find C1 and C2. Okay, we already kind of knew that. Okay, and this concept, making y, and now this new concept, y prime, making y and y prime continuous at t equals 2 pi is what helps me find the other guys. Are you guys okay with that? I mean, we just said that. Now I'm just writing it officially for you. Yeah, that idea gets you C1 and C2, but this idea gets you C3 and C4, right? Hey, that means I'm going to need y prime. I'm going to need y prime. Let's just put y prime right down here. Y prime is piecewise. It's a piecewise y prime. I'll tell you what. Wait, let's hold off a second. Let's hold off. Let's work on finding that C1 and C2. Let's see if I can do that. To find C1 and C2, I think I want to. Oh, wait a minute. I am going to need y prime, aren't I? Yeah, I'm going to. Okay, let's do y prime. I'm sorry. Y prime. The derivative of this cosine is negative 3c1 sine 3t. The derivative of that sine is a positive 3c2 cosine 3t. And then that derivative is a cosine, a 2/5 cosine 2t. Okay. All right. That's the derivative. This is y prime, and this is when I'm between 0 and 2 pi. Okay. All right, and I'll go ahead and do the bottom derivative. The bottom derivative would be kind of the same kind of thing. Negative 3c3 sine 3t and a 3c4 cosine 3t. So that's the derivative when t is greater than 2 pi. Wow. All right, I should be able to do all this. I need a little room to work, though. I'm going to get rid of this evidence. All right, so you're saying, or we're saying, or this is saying, if you plug a 0 in the function, you get a 2. And you know, and when you plug a 0 in the function, you don't plug it in the bottom piece, you plug it in the top piece. And I wonder what happens when you plug a 0 in. The cosine of 0 is a 1. So I think I get a C1. The sine of 0 is 0, so that's nothing. And the sine of 0 over there on that end is 0, so that's nothing. And what did we say? We're plugging in a 0, and it should equal 2. Well, I think I just learned that C1 is 2. That other condition says if you plug a 0 in the derivative, you get 1. Okay, I'm going to go down here. That means I go down here to the derivative. And again, though, it's the top piece of the derivative, not the bottom piece, because it's where 0, it's defined at 0. Okay, so now I'm plugging in a 0 here. Well, that term is a big 0. The cosine of 0 is 1, but that's a 3c2. And then watch out over here. When you plug in a 0, the cosine of 0 is a 1, so that's a 2/5. But a little bit of algebra, we can find c2. When I subtract 2/5, it's a 3/5. When I divide by 3, it's a 1/5. I think c2 is a 1/5. All right, we're getting there, man. We are getting there. Now, what else did we want to do? This other, that we did the initial conditions. We got C1 and C2. Yeah, we did this part. All right, so now I want to make y and y prime continuous at t equals 2 pi. Supposedly that's going to help me find C3 and C4. All right, what does that mean? That means at t equals 2 pi, I'm plugging that in here and equating that. I want y to be continuous. So at 2 pi, I'm equating that to that. Right. Okay. And I already know C1 and C2. And somehow, maybe that'll help me find C3, but I'm equating that to that at 2 pi. That's making y be continuous. Okay. So, starting at that top, C1 cosine, that's a 2. Cosine 3, and what am I doing? I'm plugging in at 2 pi. I'm just plugging in at 2 pi. And then C2 is a 1/5. That's a sine of 3 times 2 pi. Plus a 1/5 times a sine of 2 times 2 pi. I'm plugging in 2 pi, all in that top. A bunch of those are 0. That's 0. That's 0. That's 1 times 2. And it should equal the bottom at 2 pi. If you plug in a 2 pi in this bottom one, I'm going to quit writing so much. Plugging in a 2 pi in there is a 6 pi, and that's a 1. Yeah. So it's a C3, and the other guy is a 0. So I just get a C3. And I just said these are zeros. I shouldn't have wrote all that out, and this is a 1. This is a 6 pi is what it is. The cosine of 6 pi is a 1. So yeah, C3 is a 2. C3 is a 2. All right. I also need my y primes to be continuous at 2 pi. That's what I want. I want the y prime to be continuous. So that means I'm setting this equal to this at 2 pi. All right, I'm going to try to do that. Plugging a 2 pi in there is a 0. Jesus. Plugging a 2 pi in the next one is 3c2. Now hang on, it's a 3 times c2. Do I know c2? Oh, there it is. It's a 1/5. That's my 3c2. And then if I plug in a 2 pi here, cosine of 4 pi is a 1. That's a 2/5. That's a 2/5. And it should equal the bottom piece at 2 pi. At 2 pi, this sine function goes to 0. This cosine function is a 1. I think I get a 3c4. A 3c4. Wow, this is 3/5 plus 2/5. I guess that's a 1. Equals 3c4. Divide by 3, c4 is 1/3. That was fun. A lot of work here at the end, but you had to get your brain organized. It wasn't all that hard. It was nice. It was nice getting all these zeros. I like that. You're right. Officially now, I should write my official answer, which is this answer. Not this answer, right? This, the y, the y. This is my answer, but I should fill in my C1, C2, C3, and C4. Thanks for a whiteboard, I can do it like this. C1 is a 2. C2 as a 1/5. That's interesting. C3 was a 2. And C4 was a 1/3, I guess. Cool, man. That's the official piecewise answer. That was awesome. That was pretty awesome. Okay. Listen, I think there's a couple in the book, and maybe I assigned them in 4-4. 41 and 42, I see it look like piecewise problems. They kind of look like this, maybe. There's other problems with initial conditions. I haven't that are worth doing sometimes, but piecewise, I mean, made it kind of a complicated problem. You guys got any requests anywhere? Concerns? Requests? Well, let me show you this. Okay, I got something to show you. I think I'm going to show you, I'm going to talk to you about chapter 5. All this stuff is building to some applications in chapter 5. And I just would like to kind of show you how we derive these applications, sort of. So check this out, okay? I mean, this is my chapter 5 lecture, okay? But I'm doing it now instead of next week or the following week. But we'll come back and refer to this. But check this out. This is where we're headed. What we do is we do this kind of funny contrived problem where we hang a spring from the ceiling. We hang a spring from the ceiling. The spring has a natural length, L. We put a mass on that spring. When we put a mass on that spring, oops, hang on. When we put a mass on that spring, it stretches a little bit. So now, hang on here. So now it's stretched. Oh, and so now after it's stretched, it hangs here and it's in equilibrium. Equilibrium. And this is funny again, you guys. Listen to this. So we're going to call equilibrium 0. And what's funny, I know we're kind of working vertically here, but the book, all of a sudden, instead of y, we use x for position. We're going to use x for position. And so we're going to call this x equals 0. And we're going to write x as a function of time. As we get going, it's kind of funny. We're going to end up writing x as a function of time. We're going to have our x is going to be our vertical axis, and our time is our horizontal axis. I'm not sure why they do that, but I stick with them, and I do that also. We write x as a function of t. I mean, it's stupid. We could call it y, but really the truth is they're just letters anyway. Hey, here's the other thing. We're going to call above equilibrium negative. So that's negative, or x is less than 0 above that, and x is greater than 0 below that. Down is positive in these problems again. We did that once with our skydiver problem. Down is positive, up is negative above equilibrium here. I know what else is going on. Hang on. So when I hung this mass on here, it got stretched a little bit. That distance it got stretched, I'm going to call S. It got stretched this distance S. Okay. Well, then guess what we do? Somebody walks up here, grabs the mass, pulls it down, and lets it go. And then that gives us millions of d's to solve. Somebody grabs the mass, pulls it down. They either let it go, or maybe they give it a little push. I don't know what, there's some kind of maybe an initial push, but they pull it down, or maybe they push it up and let it go, or give it a push. And pulling it down and giving it a little push, those, what am I talking about? Those are initial conditions I'm talking about. When I pull it down 1 foot and then give it a push at 1 foot per second or something like that, those are initial conditions I'm talking about. But then what happens? It sets this thing into motion and it oscillates. It oscillates, but there's different ways it can oscillate depending on a lot of factors. What am I trying to do? I'm trying to develop this. This is a second order DE is what's going on here. I got to try to develop this DE. I guess when I pull this down and put it into motion, I guess I got to start analyzing the forces that are acting on this. You guys got to help me. We did this once with the skydiver, I think, but now we're doing it with this. Can we talk about the forces involved here? Okay, hold on. So he said, what's the first thing he said? Weight. Okay, he said weight. All right, you're right, that's a good force. And what is that? That's mass times gravity. Okay. That's mass times gravity. Okay, all right, that is one of the forces. Oh, hang on, and it's down, and if it's down, we'll call that positive. Okay, we're cool then. All right, what else forces do you think are acting on this? You're right. I mean, the spring, the gravity wants to pull this down, but the spring wants to pull it back up, right? And so what the book calls it is the restoring force of the spring. It's the force of the spring, but they call it the restoring force of the spring. And if we remember way back, according to Hooke's law, the force of a spring is directly proportional to the distance it is away from its natural length. Hold on. So this force is directly proportional, and that's the spring constant, by the way. It's directly proportional. I'm going to call that the spring constant. It's directly proportional to the distance it is away from equilibrium. Hold on. Not equilibrium. The distance away from its natural length, the natural length of the spring. So right now, when it's sitting here, how far is it from the natural length? S. But if you remember, this is, if it's sitting here, there's not much of a DE happening here. There's nothing happening. So you pulled it down, and now when we pulled it down, we pulled it down this initial distance, which we'll call, well, we're going to call this X. That's the distance, initial distance I pulled it down, X. So now, how far is it away from equilibrium? From natural length? S plus X. Yeah. It's that distance. Yep. All right, we're figuring this out. What you got? Any other forces you know about?
Air resistance.
Yeah, air resistance. You're right.
might be negligible.
Well, I know, it might be. And what we really mean by that is, here's what we're going to call it, because it could be air, it could be water, it could be Jell-O, whatever this is in, right? So it's called resistance or friction, or what we call it is a damping force. It's dampening or damping force. But it is just a friction or air resistance in a way, but in general, we don't call it air, we call it a damping force. And here's what we say about the damping force. We say that it's proportional, and watch this, I use beta for my constant. This is a proportionality constant. It's proportional to, I think we did this with the skydiver. The air resistance was proportional to his speed, I think. Is that how we do it? Air resistance is proportional to the speed. It's a force that's proportional to the velocity. Hey, it's proportional, and beta is a constant. It's proportional to the velocity. Now, hold on a second. This is x equals 0. These are positive x's. These are negative x's. But what is x in this problem? X is position. So can you tell me what velocity would be? X prime is velocity. Is that okay with you? So x is position, and and x prime, the derivative of position, is velocity. Yes. So I want to say this, if you don't mind. This is proportional to the velocity. I'm going to call that x prime. All right, we're doing pretty good, you guys. Let's think. What else we got going on? Any other forces? Got weight. Got the restoring force of the spring. It's going to be moving through air resistance, perhaps.
That's restoring. We just thinking about vertical.
Yeah, that's true. Everything's just vertical. Well, okay, this is a weird one, kind of. It could have a driving force. Now, that can come in a lot of forms, but like if the damn mass had a little propeller on it, a little motor on it, it could be driving itself. I mean, right? Or if it came down and we just gave it a little push every once in a while. That would be an intermittent driving force, not a constant driving force, I guess. You with me? Some kind of, it could have some kind of driving force. Now, hang on. What do we call that an external, sometimes they call it an external force, or I'm going to call it an external driving force. And here's what it is, you guys. It can come in all kinds of forms. Listen, it's just some function of t, is what we're going to call it. A function of t. All right, that's all of them, you guys. That's all the forces. Now, you know, you guys are been studying physics. What do you do when you analyze all the forces?
You sum them.
The sum of the forces, according to some guy, the sum of all the forces is
MA.
MA. Hey, and what's A?
Acceleration, x plus prime.
Yes, acceleration is A. The sum of all the forces is MA, and acceleration is A, and A is x double prime. You're right. So here we go. The sum of all the forces is MA. Here I go. MA, hang on, but I'm going to write x double prime. MA is equal to the sum of all these forces. Now wait a minute, hold on a second. The MG is good. Hey, maybe, I'm sorry, I might have screwed up here a second. I think this guy's negative.
Yeah.
Because the weight is down. I guess the restoring force of the spring is sort of back up. Yeah, well, I'll go ahead and put a negative there, but I'll also put a negative here. I'm sorry, I think this one's negative too. Because it's always opposite the direction of motion.
Yeah.
So when velocity, it's opposite the direction of motion, so it's got a negative beta x prime, and then a forcing function. Man, this is beautiful, you guys. Where do you see this? This is so beautiful. I think we just created a DE, but there's one other cool idea. There is a fact going on here. There is a true fact going on. If you stop for a second, you know, this thing is in motion, but just forget the motion for a minute. If you just analyze what's going on at equilibrium, let's analyze the forces at equilibrium for a minute. First of all, it's just hanging there, it's just sitting there. So the sum of the forces at equilibrium will not be MA. Well, it could be MA, but it's just zero. Thank you. So if I analyze the forces at equilibrium, I come up with this idea. At equilibrium, hang on. At equilibrium, the sum of the forces is zero. Now, what forces are happening at equilibrium?
The weight and restoring.
Oh, just the weight. We're not moving, so we don't have any damping force. We don't have any of this. We're just hanging there. So we got the weight. And we got this restoring force. Hang on. But I have not pulled it down x. So now the restoring force of the spring is Ks. So mg minus Ks, that's the two forces acting at equilibrium. Are you guys okay? Mm-hmm. I didn't have that extra distance x to add in there. So guess what? I've discovered this is a true fact, that mg minus Ks is zero, or you can move the Ks over and say mg equals Ks, but we can use that here in a second. If you distribute this K, mg minus Ks minus Kx, minus beta x prime plus f of t, that's 0. That's gone. Is that okay with you?
At equilibrium.
Well,
You don't have to.
hang on, you're right, hang on. At equilibrium is where we discovered this true fact. The true fact is true everywhere. That's a little tricky. I mean, we analyzed at equilibrium and came up with this true fact. And now that's just always a true fact. I guess that's my explanation. I'm trying to think of a better way to explain that. I know, I'm tempted, you're tempted, and I'm tempted to sort of say, well, this is only true at equilibrium. Well, the truth is, at equilibrium is where we discovered this fact, that mg minus ks is 0.
It's just like taking a snapshot at different positions, right?
Yeah, maybe. And so this is a snapshot here.
Yeah.
This is the easiest snapshot because all those other forces aren't there. And this snapshot reveals this truth, I guess. Yeah. All right, you guys. Maybe you can see what's coming here. But look what we got. I'm gonna watch this. This is mx double prime. Listen, I'm gonna move the beta x prime over here. It's positive beta x prime. I'm gonna move the kx over here. It's a positive kx, and it equals. I'm gonna leave the f of t over there. Look what you got. A second order dE. These are constant coefficients. M, beta, and k are constants. A second order dE, constant coefficients. Maybe non-homogeneous or maybe homogeneous, depending on whether you have a function over there. I mean, this is what we've been studying. Except it's actually, in chapter 4, we can go higher order than second order. I mean, this is classic. This is a classic. Chapter 5, second order dE. Here's the funny thing. What we're really studying is harmonic motion, we're studying this oscillating harmonic motion. We put it under. We set up this thing. Hang a mass from the ceiling. I mean, that's our model we construct to analyze this. The truth is, we're not really hanging too many masses from hanging. Hanging masses from ceilings and watching them oscillate is not exactly deep science, I guess. But it's a model for oscillating behavior that we can apply to other oscillating behaviors. I mean, let me just speculate that atoms oscillate, don't they? Kind of. This can also be applied to electrical currents. Currents can be oscillating currents, I think. Am I talking about the current?
AC currents.
Yep. I mean, the result of these are, well, there's several results, but anyway, I'll say this. Well, what we do is we start by studying what's called simple harmonic motion. And simple harmonic motion means, let's ignore damping. So we develop this formula, you guys, but then we ease into it. We start with simple harmonic motion, and then in that case, beta is 0. There's no damping. And and also we want to call it free motion. Free motion means there's no f of t. So there's no forcing function. There's no external forcing function. So we start with a very simple mx double prime plus kx equals 0. Are you guys okay? So when we start doing problems, which I know I'm not really going to do a problem today, I just wanted to prove this to you. Or develop this DE. I wanted to develop this DE like we did by analyzing the forces. That's really what I wanted to do. But once we start studying this, we start with the simple harmonic motion. This is pretty simple. I told you I don't really want to solve these, but I want to show you something. Today we already did one like this. We did this. Look at this. A y double prime plus a 9y. What's your mass? 1. What's your spring constant? 9. Are you with me? You see that? And we solved this today. And if you remember, you write your auxiliary equation. By the way, all of a sudden, if I'm in chapter 5, I'm not going to write m anymore for my auxiliary equation. Sorry. I think it'd be confusing. M is mass. I don't know. So I write my auxiliary, I write r's. R squared plus 9 equals 0. We get R equals plus or minus 3i. How do we write the answer for the DE? We write C1 cosine 3t, C2 sine 3t. Hey, guess what? I mean, that's just sine and cosine motion. That's all that is. That's a sine wave.
Oscillating, no dampening.
Right. It oscillates forever. Right. There's no damping. It oscillates forever. It's simple harmonic motion. Theoretically, it would oscillate forever. That doesn't really happen. That doesn't really happen. With a real mass and hanging from a real ceiling, there is damping. I mean, you know, the spring itself has a little dampening maybe, but it, you know, it doesn't oscillate forever. It stops eventually, of course. But in this ideal world with no damping, you're kind of in an ideal world, and you create simple harmonic motion. And it's just, all it is a sine wave or a cosine wave. We can analyze the period and yada yada. We can see how the mass and the K affect the situation. Maybe affects the amplitude and yada yada. I mean, there's a lot of things we can discuss about these relationships. But anyway, we start there. Then we add damping. We work on some of those problems. Those are interesting. And then we add the forcing function, which makes it more interesting too. But the truth is, to solve these DEs, we're going to have to use all the skills we're learning here in chapter 4. We're learning these skills of higher order DEs with constant coefficients that may or may not be homogeneous. Right. I might want to quit today. I mean, it's early. I don't know. I mean, I don't really like to quit early, but I am